Welcome to the CloudLab. So before you begin, there's two things you want to do before you log in to your data-taking session. So first of all, you will need a microphone attached to your computer so that you can talk to the CloudLab operator and tell them that you're ready to take control of the apparatus. The second thing you need is a Zoom account so that you can log in to the experiment. Any Zoom account will work, including the free ones. If you're a Kwantlen Polytechnic University student, you actually have access to Zoom through the university. So do a bit of research and get that set up ahead of time. So like I said, you need two things. One, you need a microphone attached to your computer. And two, you need a Zoom account, any Zoom account. Okay, so now I'm going to show you what it looks like when you log in to the CloudLab experiment using Zoom. So first, you would launch Zoom on your computer and log in. I've already done that. And then you want to go to the correct meeting. So your instructor will have given you a Zoom link that should automatically take you to the correct experiment when you click on it. If that doesn't work for any reason, however, you can log in directly through Zoom using the meeting ID and the passcode. But I'm going to click this meeting link and join the meeting now. And I'm going to join with video. You don't have to, but the next setting is important. You do want to join with computer audio so that you'll be able to talk to the operator. So I'll click Join with Computer Audio.
Hello, Jennifer. Welcome to the CloudLab.
Hi. And this is what things look like when you first join the experiment. One thing to notice is if you jiggle your mouse a little bit down here in this corner, there's a mute button, and over here in this corner, there's a leave button. And this little panel here where you can see people can be moved around if it's in an inconvenient location. So I'm going to ask the operator for control of the apparatus now. So hi there, operator. Could you give me control of the apparatus?
Yes, just one moment, please. And Jennifer, you have control now.
Okay, thanks so much. So now I have control of the apparatus. So first, let me give you a little explainer about what you're seeing here. So in the center, we've got this glass tube, and I'll zoom in on that later. And in front of and behind it, we've got these two copper coils. And what we're going to do is we're going to run a current through the copper coils, and that creates a magnetic field. And because these coils are circular, and there's two of them, that will create a magnetic field that's constant in direction across that glass tube in the middle. So we'll be able to change the strength of the magnetic field by changing how much current we run through the coils, but the direction will always stay constant. So let's look at that glass tube more closely now. So there is one camera with several presets, and right now we're on preset 1. So that shows the exterior of the whole apparatus. And if I go to camera preset 5, that zooms in on the tube. So now, when I turn on the heater, it's going to turn off the room lights so that we can see the electron beam better, but I'm going to explain things now while we still have the lights on. So inside this glass tube, there's three things that are important. One of them is that there's a glass ruler that runs through the center of it, and there are these little tick marks on it. And we're going to be able to read those tick marks when I zoom in even more. So we'll use this ruler to measure the diameter of the circular path that the electrons take. The other thing that's interesting is over here on the right-hand side, there's a heater which is going to heat up a piece of metal, and that boils off electrons, which is going to create a gas of free electrons inside the tube. There's also a cathode and an anode over here, and these are going to accelerate the electrons into a straight beam. So I'm going to show you that later. Now inside the glass tube itself, there's a low-pressure gas of helium, and when the electrons are accelerated through that gas, the gas starts to glow. So that's how we're going to be able to see the path that the electrons take, because we'll see the gas glowing everywhere that they passed. So as I said, here on the ruler, there's these tick marks, and they're in centimeters, and we're going to be able to measure the diameter of the electron beam in centimeters thanks to that. So if I go to preset 6, that zooms in even more, and now we can see the tick marks and read off their values. So 6, 7, 8, 9, 10, and 11, and then we can't go any larger because that's as big as the tube is. And we're going to use this later. So zooming out again, preset 5. The first thing that we're going to want to do is turn on the heater. So that's this yellow button right here. So we click that, the room lights go out, and you can actually see the heater starting to glow over here. Now there is a timer on the heater, and when it turns itself off, the room lights come back on. If that ever happens while you're working, you can just click the yellow button again, turns the heater back on, and you can just continue with your experiment. So the next thing we'll want to do is turn up the accelerating voltage. So that controls the anode and the cathode, which are right underneath the heater, and they're going to accelerate the electrons straight down. And you're going to see that. You're going to see a little blue beam of light over here on the right-hand side of the tube. So if I turn up the accelerating voltage now, you see that blue beam appear. Now, right now, the electrons are hitting the glass, which is actually not good for the glass. So fairly quickly after you turn up the accelerating voltage, you want to also turn up the coil current, which, remember, gives you a magnetic field which bends the electrons into a circle like this. And once the electrons are bent into a circle, so they're not hitting the glass anymore, then it's safe to just leave the apparatus like this. There's no longer any danger that the electron beam could damage the tube. So turn up the accelerating voltage first, and then fairly quickly turn up the coil current also until you get a full circle. Now the purpose of this experiment, so what we're trying to do, is we want to study this interplay between the radius of this circle and the accelerating voltage that's acting on the electrons, so that's the voltage that's accelerating them into a straight beam, and also the coil current, which controls the magnetic field strength, which is what bent the electrons into a circle. So those are the three things we're studying: the accelerating voltage, the magnetic field, and the radius of this circle. There's a couple of different ways in which you can do this experiment, but the basic idea is that you want to control one of those three things and watch how the other two change in relation to each other. So you could, for example, hold the magnetic field constant and study how the accelerating voltage changes the diameter of this circle. Or you could hold the accelerating voltage constant and see how the magnetic field strength changes the diameter of the circle. Or you can do what I'm going to demonstrate for you, which is that I'm going to see which combinations of accelerating voltage and magnetic field give me the same diameter for the beam every time. So I'm going to keep the diameter of the circle constant, but change the other two variables. So first I would need to choose a diameter for the electron path. So let me zoom in again. So preset 6. And I want to choose a fairly large diameter, 10 centimeters, because the percent uncertainty gets smaller when the diameter is larger. So right now, if I change my accelerating voltage, you can see I can move things up to 11 centimeters or move it back down to 10 centimeters. And I'm choosing 10 centimeters as my diameter. So I'm going to be changing the coil current and the voltage throughout the experiment, but I'm always going to want to come back to this 10 centimeters that I've chosen. It is helpful, by the way, to put the beam right on a tick mark, just because that will also help you get a smaller reading uncertainty. And another thing to be aware of is that the beam is a little dim and fuzzy when you're using small accelerating voltages. So what I'm going to do is I'm going to use a minimum voltage of about 200 volts and then go upwards from there to make my graph. So I recommend you do that as well, just because it'll give you a sharper, brighter beam to study. So I'm going to change my accelerating voltage, make it 200 to begin with, and adjust my coil current to get back down to the 10 centimeters as accurately as I can. And now we're ready to take some data. So first of all, oops, my heater came back on. So like I said, you could just click the yellow button and then continue with your experiment. So first, we record the beam diameter, so that's 10 centimeters for me, but we also need to estimate the uncertainty on this measurement. So the beam's a little bit fuzzy, there's only centimeter tick marks on the ruler. You'd have to come up with a reasonable uncertainty based on how hard you think it is to measure the beam diameter. And zooming out again just for a moment, I'll just remind you that we are measuring the diameter here, but the quantity we're actually interested in is the radius. So later, you'll divide your diameter by 2 to get the radius, and you want to also think about what you'll need to do to get the uncertainty of the radius. So that's our diameter measurement. And now we want to measure the voltage and the current of this. So to measure the voltage, you want to go to preset 4. So that gives us our beam voltage. You can see it right there. We read our voltage off of this scale as accurately as we can. So you can see the needle on the scale here. It's a little hard to see, but you can see that it's pointing pretty close to 200, which is what I set it to. So you'd read your exact value off of this scale. And what should the uncertainty on this measurement be? Well, you should estimate a reading uncertainty on this value in the usual way, based on how easy it is for you to read the needle's position off the scale. However, there's a second uncertainty that you need also. You see, there's a calibration uncertainty on this scale that comes from how it was built by the manufacturer, and you need that uncertainty also. Now, we've provided you with that uncertainty, but not here. Instead, you want to go back to the CloudLab page that is located at kpu.ca/physics/CloudLab. So that's the page that had this schedule on it, remember? So you go back to this page and you scroll down just a little bit, and right above the schedule, we've got this Documents and Specifications area. So this contains information that was given to us by the manufacturer about the voltmeter and ammeter that we're using. And you need to get the uncertainties out of this. So we're using the analog meters, not the digital meters. So you want to click on this first link. And when you get there, there's a PDF that you should open. So clicking on that, this is the information that the manufacturer gave to us about the voltmeter. And they list a calibration uncertainty of 1.5% that needs to go on your values. So again, you're going to actually have two uncertainties on your voltage. One of them is a reading uncertainty that was based on how easy it was for you to read the scale. And the second one is this instrument uncertainty due to the calibration of the voltmeter. So you'll have two uncertainties on your value. And likewise, your ammeter will also have two uncertainties. A reading uncertainty from how easy it was to read the scale, and this calibration uncertainty of 1.5%. So going back to the experiment now, we have our beam diameter and we've got our accelerating voltage off of this scale. We also need to get the coil current. So for that, we go to preset 3, and that takes us to our ammeter scale. And again, you read the value of the coil current here as accurately as you can, and you estimate a reading uncertainty on it, like before, based on how accurately you can see where the needle is pointing at the scale. And you'll also need to add a calibration uncertainty to that as well from that previous page. Now, returning to the experiment, preset 6, that's everything we need for one data point. However, we want to make a graph of our data, which means we actually need 6 to 8 different data points in total. So in my demonstration, I'm keeping the diameter constant. So for my next data point, I'd need to raise the voltage. So let's say we go to 250 volts. And then I would again adjust my coil current to get back to a 10 centimeter diameter circle. And like I said, when you're getting to higher voltages, that beam becomes easier to see. So I'd adjust both my voltage and my coil current to get 10 centimeters again. And then I would again use presets 4 to get the voltage and preset 3 to get the current, estimate uncertainties on those, and then I do it again with a larger voltage and a larger coil current until I have 6 to 8 data points in total for my graph. When you're done with everything, when you've gotten all of your data, you turn these two slider bars right to 0 and turn off the heater and go back to preset 1, and then everything is ready for the next student to come along. So at that point, then you can tell the operator that you're finished, which I'll do now. So thank you, operator. I am all finished with the equipment.
Oh, you're welcome. Come back again if you need.
You bet. And then, as a student, to log off, you can just jiggle your mouse and click this red leave button to leave the meeting. And then you can shut down Zoom when you're finished. So that's all you need to get all your data for this experiment. So good luck with the lab.